streaming. I'll pop that back up there since whoever was hopefully listening to this can copy that down. And then scroll back down to here. We're giving you the electronic structure of no core, core, and valence electrons. Would anybody like to volunteer for the no core? Sam. Would you like to come up and do it? And actually touch the pen? It is, you can rest your hand on it lightly, just so you know. It doesn't, it's not a touch screen. Hello, Ian. Very neat writing. I think I have the ability to put everything into my writing as a font. I should get you to make a font. Excellent. Since I wrote this out, I should do that. Do I have it in here? There we go, Neufeld print. There. Yeah. I do have a font that corresponds to my printing, not my writing. Okay. Now, that was a lot of work, so thank you for doing that. For the next one, I'll call someone at random. Where do we put the core? Daisy. Which one? Krypton. So, Krypton. And how much of this do we get rid of? At what point do we start? Shh, I'm trying to hear Daisy. So, 5s2. Excellent. So we can see the number of valence electrons, Ian, is how many? 4. And using it, looking at the electronic structure, why is it 4? You're not Ian. That's Ian over. Right. We have 5 and 2 electrons in there, and we have 5p2 and 2 electrons in there, and that's in the 4th energy level, so it's dropped down a little bit. We still include it when we write the electronic structure. Technically, they're still available if we run out of the S and the P, but they hardly ever get used, so we don't tend to use them in Lewis dot diagrams unless we have to. So it only has 4 valence electrons. Now, I haven't told you how to do a Lewis dot diagram. It's from last year. So a volunteer who remembers from last year, what would this look like? I've already called upon you. Yes. Oh, would you like to come up? Sure. Cross grade? You're not talking about English in this class, are you? Look, remember the only reason you take English. No, it is. You want. Oh, here. Let me do this. You want 1 in each of the 4 corners. Beautiful. It's perfect. Okay. So, I tried to click on the board. So this is the Lewis dot diagram. And as a reminder, yes? Oh, you can't do lines. Not yet. So if I did, and let's just see a few. If I have tin, I did that one. But let's say I had SB that has 5 valence electrons. You pick a coordinate. I always start at north, but it doesn't matter. And then you go around in a consistent way. So 1, 2, 3, 4, 5. I tend to start at north and go around clockwise. If you like starting at west and going counterclockwise, as long as you do it the same way around that atom, you will be fine. What you can't do is go 1, 2, 3, 4, 5, and decide to go backwards at some point. As long as you're consistent and you go around. You first separate them out because electrons don't like each other. So you remember when we have like px, py, and pz, when we put electrons in, they first are unpaired. And then we pair them up. My apologies, sir. Yes. Only because they actually wouldn't be paired yet. They separate out first. And one of the things that we don't really do this year is, you know that there's the s orbital, and then there's the 3 p's. And what they're immediately going to teach you, instead of having s and then px, py, pz, is immediately upon them, they are so close together in energy, they actually become sp, x, y, z, and let's call that w. Those aren't the real names, but they come equal, and those are the ones that go from this plus the s, and they do this thing. I think I've showed you that once before. And they point in all 4 directions. And so you end up with 4 energy levels that are identical, and they fill up 1, 2, 3, 4. So they fill up separately, and then when you have to pair them, they go opposite spin, and they pair up again. And so we're mimicking the quantum structure when we do the Lewis dot diagram, because that's how they actually bond. And then after this, it's at a later point, we'll actually be able to go into the shape. So you asked, what could you use a line? So for SB is antimony, I believe. You can now, because you can also draw this like this, SB line dot dot dot. So unpaired electrons are always dots, but these are functionally equivalent. I had a teacher who likes the German method. I had a teacher that likes lone pairs shown as separate dots. Some people like separate dots so that if you have like a molecule and say this is bonding to something, there's a difference between a bond and lone pairs. And other people like, no, all pairs should be lines, because then I remember that everything, and the other one's fine. Yep. Oh, yeah, so what we did at the beginning, how many valence electrons does tin have? You just 1, 2, skip a few, 4. This process was just to show you why we skip a few. Because we literally did 1, 2, skip a few, 4. This is the 4th energy level. These are both 5, so those are our valence electrons. Now, do you have to do that every time? No, because this would be annoying. It's mimicked on your periodic table. So if I ask you, can you tell me how many valence electrons selenium would have? Louder? 6. Yep. Underneath oxygen. So that means everything in this row has 6 valence electrons, regardless of the fact that the D ones are there. Everything this is why they share a lot of properties. And why the halogens, even though this one, you could say, well, there's all these electrons. Yeah, but it still only has 7 valence electrons, which is why it's similar to fluorine, chlorine, and iodine, and all those other things. Okay, so that's how to make a Lewis dot diagram for a single atom. Do that for sulfur, arsenic, and iodine. I'm not going, no, stop that. No. I could later, yeah, but it's also being recorded right now on live stream, so you've got it. This is also, if you're like, I did Lewis dot diagrams last year, Mr. Neufeld, you taught me Lewis dot diagrams, I know these rules. These are the rules I just went over, counting, added a route and singly, then you don't need to write that. If it's second nature now, good. If it's not second nature and you're like, I got to remember these, those are the rules. You can write them down if you'd like. Sulfur, arsenic, and what did I say the last one was? Iodine. Give me the Lewis dot diagram of each one. Iodine. I'll put it here, even though we can't see it yet, so that we know which ones we're doing. No, because if I go back, my mouse is not cooperating. There it is. If we go back, I'm going to flip back for a second. If we did tin here, right? And let's pretend I actually did do SB, so we have some differences in it. I did that. It's an atom in 3 dimensions. You can rotate it. It doesn't matter where that lone pair is, because it could be anywhere around the atom as long as they're separated. So it doesn't matter which side those are. Those can rotate. That make sense? I get 3 people to come up and do sulfur, arsenic, and iodine. Let's do. Just stop it. Chemistry E, random. We've got Jacob. And we've got Liv. And then I'll leave the third one as a surprise so that everybody still thinks they could be called. Yeah, you can first come, first serve. You can choose which one you want to do. Excellent. 2, 3, 4, 5, 6. And let's scroll down. What I'll do is, because we have iodine underneath it, we'll just erase that one and then pick. Oh, no. I thought you couldn't see the periodic table. No, it looks good. Do you know the secret yet of coming up here? The answers are all usually right there. Yeah. And then last one, Emily. If you come up and the answers aren't there, you can always definitely ask me for help as well, because I know coming up sometimes can be like, okay, am I doing it correctly? Did you want me to check first? Oh, so you're doing that one out. How many valence electrons does iodine have? Where's your periodic table? Oh, I will gift you one. What? Yeah, it is. Perfect. Now, you didn't do it the way I said, but did you do it in your head first and then you just wrote it down? Then perfect. Go up and do it. Oh, we'll be doing that. Oh, yeah. Those are, we're going to do that after this. So we're doing single atoms because I'm starting from like last year. And then we're going to work our way up. And I'm actually going to show you 2 methods. There's a method that most people show you in grade 10 that I deliberately didn't because I find it gets too popular. So we've got 6 valence electrons. So you've got 2 lone pairs. If you are drawing it German, you would go like that. And either of those is fine. Arsenic, 5 valence electrons. Again, though that could be anywhere, so as long as that looks good. And for iodine, you should just have one single electron and everything else is a pair. Questions about those? Excellent. In that case, I want you to draw a chemical reaction. Why is that there? We don't need that. I would like you underneath this to draw the Lewis dot diagram for sodium. Draw the Lewis dot diagram for chlorine, not chloride, and then draw what you think sodium chloride would look like. Do it. I always recommend you should be doing everything in pencil so that if, like, we get to here, I want you to actually attempt something, and if you get it wrong, you can correct it if you want. How many of you are doing your notes in pen? You do parts? Oh, so you can switch back and forth. Oh, okay. Max, do you want a periodic table? You want a periodic? You keep looking at there. You should have your periodic table out because it's always useful. Where's your periodic table? That's not good. You just. Well, I gave one to Max. You guys can share it. Yes? Oh, first do both of these separately. So you're missing the chlorine. Where? Oh, but you've drawn them on opposite sides. It threw me off because what you've done is you've put the reactants into either side and going in the middle. We don't do that in chemistry. Put all the reactants on the left and then make the product on the right. That is very close, though, actually. Yes? Oh, I did go over and look at Jager's, didn't I? And I set myself up. Because what I wanted to say was, what did you do right there? Yeah? Yeah, no, that's fine. But why do you have a line and a dot? Oh, okay. In that case, it's good. I'm not saying it's right, though. Yeah. But that's an intelligent thing to have done based on what you probably learned last year. I'm not saying it's wrong either, but I'm not saying it's right. Yeah, excellent. Because I have heard of people who look. Oh, you put them all the way around it like that. That's actually fairly clever. But this is what type of bonding is this? Ionic or covalent? Ionic. So the chlorine's actually going to steal that electron. It is not going to give any. So sodium should end up with none. No, actually, very close. And I've already looked at yours. Why does sodium have two? It had one. Does it get another one? What type of bonding is ionic or covalent? Metal and a non-metal. Ionic. So someone, probably chlorine, is going to steal the electron from sodium, and they're going to end up with none. Oh, that's not bad. I'm always interested to see what people come up with. What type of bonding is this? Ionic. So that means electrons move. So they don't share, so they can't be around the whole thing. There's no sharing, no happy hand holding, nothing. Yeah, oh, that's not bad. That's not bad. Oh, it's not perfectly right, no. But that's okay. Oh, I'll show you. Do you have too many how many electrons are in a bond? 2. So why do you have a single electron there? What do you guys got? Oh, that's not bad. You even drew a little arrow to show where it goes. That's not bad. That's pretty good. Yeah. Okay, I saw a lot of good ones. I saw some really fanciful ones. I really like, I'll show you some of the ones I really liked. Now, most people started off sodium, 1 electron, go somewhere. Chlorine, how many electrons? 7. So most people, I think everybody that I saw, whoops, I did the E thing, did this. Great. And then it was like, how do they combine? The ones that went like this, love that. It's wrong, but I love it because it's like putting them together. It's like they're a happy family. Like, shouldn't they be bonded like that? If I had to like rule the universe and I got to dictate the laws of physics, that's how they should bond, but they don't. Covalent bonding, metal and a non-metal. So chlorine, here, why don't I make this really obvious? And we'll make sodium red. Is ion, did I say covalent? I said the opposite of what I meant. Sometimes I do that. Metal and a non-metal, ionic bonding, not covalent. And of course, what's going to happen is that in ionic bonding, electrons move from one to the other and they're attracted by their charge. So that electron ends up over there. They don't share. So sodium ends up sad and alone with no electrons. However, what does sodium now have that it didn't have before? It's positive. So we just write a little positive sign there. So those of you who wrote it correctly, that's the only thing you're missing. Although we do something a little special with chlorine, because now chlorine has all of the, and what's its charge? Negative. So we put it in square brackets. If you put both of them in square brackets, is that what you said? Yeah, but then they don't have a charge because +1 - 1 is 0. So if you go like NaCl square brackets, it would have to be. Oh, you did. Yeah, that's fine. Yeah. The reason we put square brackets is so that you know that that -1 is not due to any specific electron, and we're separating the electronic structure from the charge because the charge applies to the whole thing. So we don't want to say like that -1 is specifically up here or anything. So we use, now you don't, the reason I didn't draw it here is because you don't need it. There's no electrons in sodium. Sodium is sad and alone. So that is good. So this is the electronic structure if you were to do an ionic compound. We don't often do them for ionic compounds or single compounds. It's really powerful when we use them for covalent. But you can see them occasionally, and people like to do them when they want to show how electrons transfer. So that's to show literally this. And you're done. It doesn't get more complicated than that, other than if you get like 2, you could have CaCl2, and then you would have 2 electrons being donated by calcium, and you'd end up with 2 chlorines, and you just show that. Where it really takes charge is for compounds. Now, there's a lot of rules, and I find the rules really help later on, and this is the method if you had me last year that I taught you, and now I'm going to show you the other method, because I want you to do H2O just how you think it should be done. Just, I want you to draw, give me the Lewis for hydrogen, give me the Lewis for the other hydrogen, because it's H2, and give me the Lewis for oxygen. Oh, no, I'm going to say, right now we're going to say forget the rules. I will do the rules, and then we'll go back to it. But there's actually 2 ways to do it, and for really simple ones, you can say no rules. But then when you get to more complicated ones, the rules, if doing it by the rules, will be actually quite important. And there are cases that if you follow the rules, they don't work very well, and it's actually easier to do it this way. So I want you to now be able to do it both and flip back and forth. So hydrogen's a really easy one. I'm going to show you to do it. Just do the Lewis dot diagram for hydrogen and oxygen. Yes, hand. Why is there only 2 electrons for oxygen? helium. If it was helium, oh, yeah, see, you asked the one I don't like. I told you to go around in coordinates of the compass, right? So if oxygen had only 2, which it doesn't, but if it did, it would look like that. But if it's helium, it would look like this. Yeah, but the reason for that, and I can now tell you the reason, because I was teaching this to someone who was in grade 9, and they didn't know why. What orbital does helium have? One s. It's in the s orbital. How many electrons fit in an s? 2. So they literally go in this and then that, and then they're paired, and then they're together. So for helium, they are paired, but we never discuss helium because it doesn't bond. Whereas oxygen, you have that S and P, and so they all separate out, and then they all go together. So helium is that exception to like the 4 corners. They actually share, right. So on the other one, I didn't mention this. On the other one, there were a lot of people that did this. They made a bond. And I would say you don't do that, because they're not bonded directly. It's only their charge. Now, having said that, has anybody in this room had a teacher previously tell them that you do that? Different school? Yes. That is taught in some schools. They will teach you to do that because they want you to get used to bonding. And I can't say it's wrong. There are textbooks that will do that too. I don't like it because if you go like this, it really implies this is a covalent bond, and they're bonded through that, but they're actually bonded by the charges. And so it can lead to confusion. So I don't do that. However, knowing that, apparently I'm not in control of all of education in the entire world or the universe or physical laws, I will accept it if you did it on a test. So things you previously learned still count. And I've seen that before by lots of students, which is why I asked that. So if you did it that way, you weren't wrong. I just don't like it. Yes. 1 second. I want people's versions of this. Why don't I just should I call 3 people up? 2 people, because the hydrogens are both the same. Sahaj and Max. First come, first serve for hydrogen or oxygen. Which means Max got there first. He's a lot closer. Well done, Max. Excellent. He did twice as much work, though. Yeah. Oh, I did. Hold it. I switched pages. Right. And the answers aren't in this either, because I erased it. What do you got? How many single electrons do you think there should be? Shh. No, don't. Stop that. Sam. There are 6 electrons in total, so just start going around. Oh. Yeah, no, just make a dot. It should be on it. Yeah. Oh, yeah. Okay, pair. Yeah, that'll work. Oh, too many. Why is it not working? Oh, I've done something weird. There you go. Another single one right there. Excellent. You're welcome. And the reason the answers aren't there is because we then do something like this. This is called solving a Lewis dot diagram by inspection, which literally means you look at it and you just make it up based on what makes sense. If things are paired, they don't like to be separated. If they're unpaired, they'd really like to find a partner. How should this go? Yes? Both the hydrogens go on either side. So, where? Here, here, here. There? Okay. And the other one on the bottom, perfect. And I'll rotate that. And then, yeah, where they bonded, you say, oh, these are lines. So we go oxygen, dot, 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 dot. We can keep those hydrogens and hydrogens. Now, if you did this, or any other configuration, that's all fine, because it's three-dimensional. This is actually the same as that rotated towards you. We haven't done too much as shapes. Yes? You're going to ask about that. So that's H2O. Here's how you do it. Now, that's by inspection, and there are cases you're going to be doing that. And we already know the answer. So we're going to do the other method that has rules, and I'll show you the rules. It's a bit more complicated. Now, so I'm just going to show it to you. H2O. The first thing I want is the valence of electrons from 2 hydrogens and 1 oxygen, and for any charges. Yeah, we did this last year. How many valence electrons do I have from 2 hydrogens? 2. How many from 1 oxygen? 6. How many from its charge? It's a trick question. Does it have a charge? No. Did you say that? You quietly said, then that was correct. Well done. Say it louder, remember, confidence will make you president of the United States someday. It doesn't matter. As far as I know, someone told me very reliably that Obama didn't even have a U.S. birth certificate. That he was president. And the person who said that he didn't have a birth certificate became president next because he was so confident about it. So I'm pretty sure all you need is confidence. Say whatever you want with perfect confidence. Hold it. An entire country trusted Donald Trump. Are you doubting the word of a president? who was, oh, and according to the same people, still is president. Yeah. Oh. As probably his dad was very, very wealthy, but so was his grandpa, so it could be either. Yeah. 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 That would explain it. Okay, moving on, away from Trump. Sorry, I distracted everybody. We then add up. Oh, if this was a +1 charge, let's just pretend it was. What would I do to the number of electrons? I would add 1. I'd -1, because if it's positive, you have to take away some of the negative. If it would have had a -2 charge, what would I do to the number of electrons? Add them. So whatever the charge is, you have to add or take away. You have to like reverse it to add or take away. But there's no charge, so we're not going to do that, and I'll get rid of that, and we'll go like this. And you add up 2, 6, and we go 8. Now, all those electrons are gone. We don't consider them as belonging to any particular atom. This method works really well if you're going to end up with double or triple bonds or weird structures. So other than simple ones like hydrogen, this one works better. We take the electrons away from everybody, and then we distribute them. We put the central atom in the middle. Which is the central atom? Oxygen. So we put it in the middle. And then we put the outer atoms on the outside. H and H. Because there's only one of it. That's literally the only reason. And then we bond them. So we bond every outer atom to the central one. How many electrons did I use up doing that? 4. So we are also keeping track, and I'm going to look for your work and make sure you get to 0. You have to keep track every step. So now that I've done that, the next step is to give the outer atoms their full octet if they require it. Does hydrogen require an octet? How many does it require? Oh, 8 electrons. Hydrogen is happy with how many? 1, 2. Because it's in the s orbital like helium is, so it only needs 2. So hydrogen is an exception to what we're going to call the octet rule, which means everything wants 8 electrons. So hydrogen is an exception. If you can't fill it with electrons, you'd start there first, but if you can't, then you put all the remaining electrons in pairs on the central atom. How many pairs do we have left? 2. So we put on 2 pairs where they fit. And then we minus them away, and we have 0 electrons. And then we inspect. Is oxygen happy? Yes. If it wasn't happy, if it didn't have 8, let's say it only has 6, then we'd start taking electrons from its neighboring atoms and making double bonds and triple bonds and doing things like that. And this is to make sure that we stop adding electrons when we run out. Okay? Hazel? You said what? Why does what need 2? Oh, hydrogen is an exception to the octet rule because go back to Bohr. How many electrons in the first shell? And for our new model, the first shell is S, 1s, 1s, 2. So, yeah. Okay. So all the rules I just said are these ones. Now, if this whole time you've been like, I remember this from last year so well, Mr. Neufeld, you don't need to write this down. But if you do need to write this down, here it is. And remember, should you be writing this down word for word? Yeah, that's the rote reply I'm expecting. If you don't believe me, I will write down what I would write down if I was a student like you, or I was back in like third-year university. Lewis dot rules. 1. What is it you need? No, you're reading out. Is there something not displaying that should be displayed? Oh, good. Oh, so you don't start putting in double bonds now. So you bond the central atom to the outer atoms with just one bond. Boom, 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 boom. So when we went here, down here with water, I just bonded it with one bond each, right? I don't want you to go crazy and start going like, because you just felt like it. Hazel, do you need glasses? Hazel? Do you have your contacts? Should you have contacts? Do you normally have glasses? Are you lying? It's a what? Oh, you're writing this down. But this is that. This is my interpretation of that in shorter form, what I would write that's understandable by me, and I'm going to go over it. Because if you're writing yours, it should be understandable by you. And certainly you might be using more words because you're not as used to taking non-verbatim notes. There's two. Because my interpretation of this is, if I was writing this down for my own brain, I would say, this says count valence electrons. Add them up. For every positive charge, you take away one. For every negative charge, you add one. This is to the electrons. But I'll remember that. You might not remember that. You might want to add electrons. I don't know. So this is very explicit, but it's also very long. So you want to shorten it so that the parts you're going to remember, you can take out. 2, put the central in the center. Bond them, 2 electrons per. The outer rim first. And I say outer rim because I play a video game where they talk about the outer rim planets, and so that makes like sense in my brain. I'll go, oh yeah, don't do the center ones first. Electrons in pairs to an octet. And then last one, put in double bonds and triple bonds if the central atom is unhappy. And I'll know that unhappy means it doesn't have an octet. So that is my version of the rules if this is my personal set of notes. The central sad face. Yeah. But I am not saying you should write this, because that is very personal to me. I know what that means. It's also personal to me after having, taught chemistry and getting a chemistry degree. And if I was learning the rules for the first time, this would be sufficient for me. You might use a few more. You might use different things. You might use color. Also, I put some definitions down there just so that we can be on the same page. Some definitions. What do we mean when we say octet rule and lone pair? Because I've just started saying them. They are a bit from last year. And as a method, this will work really well, especially in grade 11, for any atom that just has a central, any molecule that has a central atom. This will work incredibly well. You do have to follow the steps rigorously, like you're playing Magic the card game. Like the rules are interpreted in order and in that exact order. You first put it in the center, then you put the ones on the outside, then you bond them in single bonds, then you put the electrons on the outside. And if you do it, read through and do it exactly, you will have no problems. Getting used to doing it in that order is usually kind of the problem. I am going to stop me or scream if I'm like going too far. Our definitions: lone pairs, non-bonding valence electrons. Octet rule: each atom in certain families, which are essentially these families. And actually mostly only these ones. So there's like 4 or 5 families that this is true. But it's not, again, the amount, the number of different families. It's the fact that those are the chemicals of life, and almost all our chemistry deals with them. So the octet rules actually works out most of the time, because you're usually dealing with things that do obey the octet rule. Our first exception is hydrogen. We are going to do more exceptions later. There are many exceptions, like most of the periodic table. It just is. Well, first of all the metals are an exception. But if you're doing covalent bonding, you don't touch the metals. So already we're restricting ourselves to here. None of the noble gases will bond, so we don't include those. All of the halogens will do the octet rule, so these ones and those ones. So really the ones that don't, that we'll ever see, are like here. So it's not so much that the entire periodic table will violate it. It's like, of the ones you'll see, most of them actually will do it. I am reminded, it's like the difference between quantity and dose. I'm reminded of a scary anti-chemistry TikTok I saw the other day, where this person, a nutritionist, was like, here's the list of fruits and vegetables that contain too many pesticides, and you should never eat them. Have you heard that, like the dirty dozen? It's not a thing. They don't count the amount of each pesticide that is on the fruit. And they exclude organic food entirely as a category, which also has pesticides on it. So there's a dose required to become a poison, and the amount that they detect is like a very, very small amount of that dose. Like they're well below the limits. They're just literally counting the number so they can come up with a scary number. Not how much of it is there. If you have a fruit and it had pesticide, only one type, but it had so much on it it would kill you, it wouldn't make it into the dirty dozen because they don't care about the dose when they come up with that list. It's a nutritionist scare list. Oh yeah, and if you're worried about it, rinse your fruits and vegetables and they go away. Yeah. There's a difference, by the way, between a nutritionist and a dietitian. A dietitian is a legally protected term that you must have a degree to claim that you have, and you have to have graduated from an accredited university. A nutritionist is someone who says that they're a nutritionist. It is not a legally protected term. You could say you're a nutritionist right now, and there's nothing anybody could do to say that you're not, other than disagree with your point of view. That doesn't mean all nutritionists are bad, by the way. I want to emphasize that too. It just means it's not legally protected. So anybody can call themselves a nutritionist. There are some people out there that call themselves nutritionists who are actually very good at what they do. They're just not dietitians. I would like you to do this one using the rules I told you. And I want to see you make that valence electron count process. And I want to make sure, because 11:45, I'm going to run around and just see how you're doing it. Don't do it that way. Nope. No, that's the first way. I want you to do it where you write out the valence electrons. So just to start you off, it's like the second way. We have nitrogen, we have 4 hydrogens, and we have a +1 charge. Put the number of electrons in each and add them up. Then put in the central atom, follow through the rules. Excellent. Hold it. How did you go 5 + 4 + 1 and get 8? You were right, but I don't know how you got to be right. But why'd you say -1 if you wrote +1? That's the charge. Write the charge on this side. Put the amount of electrons on that side. So write -1. There you go. Otherwise, you're definitely going to confuse my brain. Nope. You've done it by inspection, which is the first method. I want you to do it that way, where you actually count out the electrons. Because I'm going to give you progressively harder and harder examples. Yeah, that is good. That's exactly what. So what's step 2? No, like on the rules, what's step 2? Bond outer atoms to center. And I just want to see your electron counting, and that you're doing the process. Excellent. Boom, boom, boom. Excellent. Boom, boom, boom. You counted them up, put them away. No, you're trying to do it the first method. Write down the N for H + 1, count the number of valence electrons. Put this away, because that will only give you answers rather than working through the process. Right, so if you have a +1 charge, what does that do to the number of electrons? Yeah, so you write -1 beside it. Not there, right under here for the counting the electrons. Just write, write down -1. Now add them all up. What do you get? 8. There, that's how you count electrons. Now do the structure with the central atom. Yep, perfect. You can do that. I'll accept it, because I know other areas in the world, and sometimes even in this very building, there are teachers that will allow that. It's just ionic bonds, yeah, because they're actually attracted by their charges, not by the bond. Yeah. No, I want to. Little line, write it underneath, like, show your work like a mathematical process. Can I quickly see yours before you go? It's right, yeah. Did you count the valence electrons? Oh, how many electrons are in hydrogen? Just one hydrogen. No, it wants to, but how many does it have as valence electrons? Yeah, and you have 4 of them, so it has 4. So 5 plus 4 minus 1 is 8. Is that better? Okay. Before you go, sorry, I'm not going to let you go yet. I would like you to do CO2 for homework. I just want you to, using that process. If you haven't done NH4 yet, do that one for homework, and then just try CO2. I will do it next day. We'll go over it next day. It'll be fine. But I just want you to attempt it. Thank you. Thank you. Thank you. Who is in here next? No, I said there shouldn't be. What I'm going to do is I'm going to put it on a Google Classroom thing, and I'll copy and paste it in there. You should just have a signature.